Come on in, everyone. I'm just trying to get some stuff in order to start class. Feel free to ask me any questions if you have any yet.
Hi, Professor.
Yes.
You never replied to my email.
Yeah, actually, I was looking for your name. I remember last week I told you I was going to give you extension, and I couldn't find your name. Is your name listed under a different name within my course than what's showing here on Zoom?
Yeah, the first time, but I think I corrected that one since the first
Okay.
time.
So, but it is the same last name then.
Yes,
Okay, yeah. Well, I
DOH,
didn't see
yeah.
the first name. I didn't even look, but yeah, I will correct that. I apologize for it taking so long, but I literally I started thinking, well, maybe you might have been a student from one of my other classes. So I started looking at some of my other classes, including at other schools. So I'm sorry. I will make that straight with you as soon as possible. But
Thank you.
I apologize. Don't worry, it will not harm you.
Thank you, Professor.
You're welcome. Sorry again. Anybody else have a question that my senile butt can help? I've had quite a bit of fun today picking on myself from my students. Uh, the young people, they really like it when I get down and speak at their level. Nah, just joking. That was actually somewhat of a quote from Real Genius. I don't know if y'all ever saw that, but that is a definite thing that you're gonna have to watch if you're gonna continue to be a part of my class. I'm just saying. The student. Okay. I have no idea where I'm at now. Oh yeah, there we are. Does anybody have any questions? We still got about, well, heck, we got like 6 minutes left, and I got 6 of you folks in here already. Isn't that great? And there goes my watch reminding me it's time to log in. Oh boy. I finally got that set up. Looks like I got all the students in here that's gotten here. I just made, of course, you had a test that was due last night, 11:59 p.m. Mr. Dowdy, did you manage to make that one, or should I give you some assistance in that as well? I know we have sometimes students miss some tests, and I'm in light of me not always being up to speed on getting everything done on time, like for instance, grading lab reports. I'm usually a little more generous than a lot of instructors on deadlines. So if y'all missed a test, which you shouldn't do, of course, I never ever want my students to miss a test. But still, if you miss a test, I'd rather you miss a test, let me know, and let me get you made up real quick rather than just let you get a 0 or drop you uh like a lot of people will. Generally speaking, the college motto is if the student skips a test, you just go ahead and drop them, or her, or them, or whatever. So I don't want to be that person, and what I really want to do is get y'all transitioning from whatever life you had in grade school to whatever life you might end up in, whether it be a trade school, a certificate program that you're in here, or an actual college transfer slash university transfer slash graduate school, which, obviously you'd have to go to a 4-year school before going to grad school, but still, I would really like to just help you guys in transitioning to that. Mainly because I was such a deadbeat in school that everything was a shock to me. So I assume everybody can be as unfortunate or even less fortunate than I was, and I just want to help. So, and sometimes I just can't stand quietness, so I just talk for no reason but to talk. I got my Pushing cat on again today. Check him out. I think he's doing a wiggle, wiggle, wiggle. With his little paws. All right. So as I was saying, we do have a test that's due on the 19th. So that's a week from yesterday. We had one that was due last night, 11:59 p.m. Again, make sure you let me know if you missed that. I will make some kind of arrangements where I can, reward those who made it on time, and then still get those who might have forgotten to do it or missed it. Still make a chance for them to do well. So that's one thing. Another thing is I went ahead and opened up chapters 5 and chapter 6 practice. That those are things that don't count in any way on your grade book. It's just that I've had students ask for those in the past in addition to practice tests. So the practice tests will still come, but I've got those up now for chapters 5 and 6. And I've covered Newton's laws of motions last time, but now I'm going to actually go ahead and do some more direct applications. So far we've done things like with free body diagrams, just getting you used to what you have to do with those. And now I'm going to show you not only more free body diagrams, but more complex problems, and give you some, it really is somewhat a bit of mathematical techniques that you sort of have experience with from algebra, but some of which you definitely would not have learned in algebra. And for good reason, but in the physics world, we do some of these tricks quite often, specifically because we know in many cases that it's not going to be a problem mathematically, even though it's sort of frowned upon in the mathematics community. So you'll see hopefully one of those problems today.
One of what problems? Sorry, I just joined in.
I was just saying, for instance, there's a problem today. I usually call it the fuzzy dice problem, where you have, like, let's say fuzzy dice hanging from a rearview mirror in your car. It turns out if you hit the accelerator, that fuzzy die is going to roll back like this, and you can use that angle that it makes with the vertical to figure out the acceleration of your vehicle. But to do that, well, there's a lot of ways you can do it, but there's one way that's really, really easy and quick to do it, but it's a kind of mathematical trick that I never recall any of my math teachers teaching me. Yet it's a common thing for us to do in quantum mechanics as well as in Newtonian mechanics and stuff like that. We just do a lot of different things. Taylor series, Maclaurin series expansions, we're always doing those. We never do tests for convergence and stuff like that, specifically because most of the time physical conditions that have to be met in order for a something like conversion to occur, that is almost always met by the physical needs of the situation. So we just don't worry too much about that. Of course, we always got to keep in mind that, hey, we're skipping this. In fact, my PhD advisor at Chapel Hill somewhat became famous for doing just that. Specifically, we were in the process of transforming Einstein's equations into hyperbolic form as opposed to elliptical form, or vice versa. I can't even remember now. It's been so long. But everybody that tried to do it had always made this one assumption that we've made for years. But he took a deeper look at it and said, I don't think we can make that assumption, and ended up being really something that helped us transform Einstein's equations into a set of equations that were more easily soluble, but also made more sense because it didn't have the speed of light it didn't have objects propagating at faster than the speed of light, which obviously would be a problem with relativity, period. So anyways, there's a lot of times where we have to do that. So that's one of the big things in science in general is, for instance, we just put out the James Webb Space Telescope, and one of the first things they said was, hey, the first thing we're going to do with this is verify our what we call our distance ladder. So we use a certain type of technique to measure things within our solar system, and then we use the data that we got from our things in the solar system to make other approximations to make further distances, and then we make other distances approximated based on that. But when we get something new that can give us even more precision, Then we go back and double check and make sure this first thing that led us to out of the solar system works, and then check that thing that was out of the solar system and allowed us to go to the next level, make sure that works. So that's just an ongoing thing with science. You can't just assume it's done. You always have to look for maybe someone's forgot something, or maybe we're doing something that we didn't realize we're doing, and we need to check it again. So. All right, well, it's definitely time for class to start. So I'm going to ask again, we got a good 20 students in here. Does anyone have any specific questions you'd like to ask regarding homework problems, regarding chapters 1 through 5, or anything else for that matter? And again, I did announce that we had a test due last night, 11:59. We got another one due this coming Sunday, and I'm probably going to put up test 3 really soon as well. And I already put up chapters 5 and 6 practice, so you guys can do those. They don't count for anything. Remember, the practice tests for the individual tests and for the midterm and for the final, they actually count. And if you don't do one of them before the test, then you get a 0 for that particular practice test, and that's averaged in with all the other practice tests with no dropping. And whatever the average score of all those practice tests is at the end of the semester, I divide that grade by 20 and add it to your course grade. So there's definitely a strong impetus, a good reason for you, not only the fact that you can do a lot better on your test by doing it, but also because you can actually do better in the course by actually getting extra credit points by doing it. So no questions. I don't see any popping up on chat or otherwise. And still got people coming in. Yes,
you said you made an announcement last night.
Oh, I said no. We had a test that was due last night. Sorry. Yeah.
Which test was that?
Test 1, February 12th at 11:59 p.m.
Oh, okay.
Probably one you already did. In other words, and in fact, I kept extending it. But the test 2, which for you guys I think covers 3 and 4, that's due this coming Sunday, which is plenty of time. I mean, we're already sort of in 5 and 6. I'll just put it that way, because I don't necessarily cover with the same examples that your book does, but I have some very specific examples that I like to cover. So I just want to make sure you guys understand Newton's laws of motion. I want you to generally know that, hey, if you have a chapter or 5 or 3 or 2 that have, such and such law in the name or as the name, there's a high probability that you need to take such and such names law and memorize them, including memorize the actual names. For instance, it's not unreasonable for me to ask you on a final exam without access to you writing this down on your equation sheet, but what is Newton's first law of motion? What is Newton's second law of motion? Or what is Newton's third law of motion? So not only do you need to know those laws, but you need to know which one's called which. Same thing with Kepler's laws of motion, same thing with Kirchhoff's loop rule or Kirchhoff's junction rule. So big things like that are supposed to be chucker questions for us instructors. So we put something like that and it's like a gift, but then we get the test back and we find out that, out of 24 students, 22 of them didn't know the answer. And we're like, so keep that in mind, guys. Next semester, for instance, you're in 242, whenever you do decide to take it. We're going to cover Maxwell's equations, and quite often one of the questions on the final exam is state Maxwell's 4 equations. So that's just something you should always be prepared to do. So it looks like we've got 22 people in here now, and I'm going to go ahead and get started. So the lab we're doing this week, or you might be doing in the future anyways, is on the Atwood Machine, and the Atwood Machine is a really, really good problem. And not only that, there's a lot of ways we can soup it up to make it even more complex, but more interesting of a problem. And not only that, the results come back and turn out to have a really, really good resemblance to some other results that we'll learn later when we talk about head-on collisions in one dimension with conservation of momentum. Literally the same equations and forms. So that's kind of nice. Just like we had the same equations for the equivalent resistance. If they're all in series, we have exactly the same equivalent to all capacitors, all in parallel, or vice versa. So things like that just pop up over and over again. So that's kind of neat. So let me start off by solving a problem, or posing a problem called Atwood's Machine. And in the Atwood's Machine, which is basically a pulley with a rope hanging over both sides, one mass and another mass on the other side. Obviously, normally one mass is bigger than the other. Obviously, since it's bigger than the other, it's going to tend to lift the other up. So that's the problem we're trying to solve. What we're going to solve for is the acceleration of the system, and two, the tension in the ropes. And we're going to go over some very tough physics and figure out some really cool stuff that are actual physical principles. So I'm going to go ahead and share my screen, barring anyone with a question. Okay, it looks like everybody's ready to roll. Let's share the screen now. Share the screen. Still waiting to share the screen. No, I'm not in Virginia Beach, but it does sound like it because the jet's definitely going by. Okay, so this problem is called the Atwood Machine. Okay, basically what it is, and I'm going to make simplifications, but basically what it is a pulley to which two masses are actually tied. Let's say this mass right here is a mass big M, and this mass right here, let's say is a mass little m. Now, what I'm going to do is I'm going to be working this problem completely in terms of symbols. And I do that a lot. You've probably already noticed that, in fact. That is very much a theoretical physicist sort of thing to do. It's not something that you're really required to do, except in some circumstances, like when we start doing trying to integrate to get the center of mass or something like that. Then we find out that's probably a pretty good time to play around with some things and stuff like that. But the main thing is I do it because when I've solved a problem like the Atwood machine for acceleration and tension, by using just symbols inside of it instead of actual physical numbers, then I've actually solved an infinity of problems as opposed to just, you know, a problem. But if I put in numbers, then I've essentially just solved for that specific problem, and that's it. So that's my reasoning for it. Not only that, at the end, I get a formula in terms of things I know, and I can analyze that and see if it makes physical sense, and also maybe learn what is something that makes physical sense, you know. So let's start off with this. So with the Atwood machine, what I want to know is the acceleration of each block, A equals question mark. And I haven't made the argument yet, but there should be exactly one A for these. And there should be exactly one tension for these. And I haven't made that argument yet either. But I am going to assume, the pulley and cord / string are massless. And I'm going to say plus there's no friction. So there's no friction in the pulley or anything like that. That's what I'm talking about. Now, you'll see as time goes on exactly why I made such arguments or such assumptions. And it's very easy to meet such a standard. You just, you know, use a pulley that weighs a lot less, say, than the masses you're hanging. Use rope that weighs a lot less, say, than the masses that you're hanging. So for instance, if I took two styrofoam rectangular solids and then hung a big, you know, huge chain like you tie up an aircraft carrier with across a pulley, then obviously the strings are not massless in that case. In fact, the strings are more part of the mass than the actual masses themselves. So we're doing this kind of stuff, imagining extremes like styrofoam blocks and aircraft carrier chains as the extremes to get you to understand, oh, in the extreme sense, then yeah, the chain could weigh so much that the masses don't matter. And that's the way we analyze in physics, is we take things and look at the most extreme cases, and then make sure they make sense with what you'd expect. Or if you find out that you've done all the work correctly and repeatedly found no error, then you have to check your sense of what's right and what's wrong physically just to make up for it. So what I'm first going to do is tell you that when we solve systems, or when we solve equations like the equation of motion, which is called Newton's second law, we have to use free body diagrams. We've already learned about that. We have to break the forces down into vector components parallel to the axes. We've already talked about that. But one of the things that we want to do is we got to be careful in what we actually say is the object. Like if we're going to use Newton's second law, which says it's summation of all the forces acting on a body of mass m is equal to m times the object's acceleration, where the acceleration is actually parallel to the net force. If I chose to make the mass in this case, or the object in this case, the little mass little m plus the string plus the mass big M, I could actually do that, but that's going to present a whole buttload of problems. And not only that, it's going to prevent me from solving for the tension, because if I treat mass little m, mass big M, and the string that's connecting them as one big object, then the tension is an internal force and therefore can't be used on the left-hand side of the equation of motion, i.e. Newton's second law. Okay, so that's one thing. Another thing is when I try to make up multiple systems to solve, like in this case, I'm going to do a free body diagram for mass little m. I'm going to do a free body diagram for mass big M. I'm going to make F equals MA for both of those, that sort of thing. But when I do that, I'm going to try to choose coordinates that are consistent so that I don't have to make up weird equations like the acceleration of little m is the negative of the acceleration of big M. Okay. In other words, if I choose one direction as positive, I got to do the equivalent direction on the other side as positive as well to keep from running into problems. Another thing that I'm going to do here, of course, is I am going to assume that the two tensions are equal. And the reason why I can do that is because the pulley is essentially massless and frictionless. What does that mean? That means, well, for instance, mass little m could be 10 kilograms, and the mass of the pulley would probably have some decent bearings for starters, so that would get rid of the idea of friction. But if the pulley was less than even let's say 1 kilogram, then I would probably be pretty safe in assuming that the pulley was massless, because the smallest mass, little m, is a factor of 10 bigger than the mass of the pulley. Now, if you wanted to think a little bit about tension in the rope, what you need to think about is let's imagine the extremes and see why, in this case, saying a massless pulley with frictionless hub allows us to have tensions that are equal. You could consider, instead of just a regular pulley, imagine a pulley being made out of a concrete, let's say, pole. So we have a concrete pole that's going into the screen and out of the screen, and about midway from one end to the other, we got a loop of rope over top of it with these masses hanging from it, and that pole is going to be made of concrete, which is obviously very heavy, and it's going to be, let's say, 10 inches in diameter. That sucker is heavy, and it's going to take a buttload of force to actually try to rotate it. So if big M was big enough to actually cause that long, big, heavy, cylindrical pulley to rotate, then I think you would reach the conclusion that the tension that's attached to the mass big M would be responsible not only for holding up the mass big M from falling at a rate of 9.8, but it would also be responsible for rotating that big, heavy hunk of concrete that's the pulley. Whereas the tension on the other side, on the little m, all that's required to do is lift the mass little m at the same acceleration that the mass big M has, or at least same in magnitude. So I think you can see from that extreme case of a super, super, super heavy pulley that you would definitely have a tension left and a tension right, and they would be different. So by us choosing it to be a massless pulley and massless cord / string and a frictionless pulley, we see no reason to have the tensions be different. The other thing I'm going to do is I'm going to choose a coordinate system, again, that's consistent, and I'm going to do something smart with that. So first off, let's consider mass little m. So mass little m is the first part of the problem we're going to solve. And what I mean by mass little m is I'm going to make an equation of motion for the mass little m. And to do that, I am going to make a coordinate system. And the way I drew this, the big M is up high, the little m is down low, and the big M looks like I'm trying to say, hey, that big mass M is going to lift that little mass little m. And in fact, it's likely for the big mass, or the mass big M, to go down and the mass little m to go up. So what I'm going to do is I'm going to say little m going up is the positive direction. And the way I do that is I just make a y-axis like that. And then I draw a little dot for the mass little m. And now I draw all the forces acting on it. And I use blue, for instance, for the positive direction and red for the negative direction. Again, this is the positive y-axis going up. Now notice if the mass little m goes up, the mass big M is going to go down. So when I make a coordinate system for the big M, I'm going to have down be the positive direction. That way I don't have to make up any goofy equations like a little m is equal to negative a big M. Okay. So can anybody tell me any forces that might actually be acting on the mass big M? Or excuse me, little m.
The big M times gravity.
Exactly.
Pulling it upward.
Exactly. What I was telling my students today is when you're going to make a free body diagram, the first thing you want to do is say almost the only thing that can apply a force to an object are things touching it. And then once you're finished with all those things, then you jump to the weird forces, which are what we call action at a distance, or forces that can act without touching. And obviously the one we know of is gravity. The earth is going to pull on this mass without physically touching this mass. Okay. Other examples as the semesters progress would be electric force or magnetic force, or if we got into atomic physics, it'd be the strong nuclear force or the weak nuclear force. But generally speaking, forces that have to reach across a distance are ones you have to consider, but normally I go through the things touching it first. But you've already said it, the actual force of gravity, which is pulling the mass little m downward, that's the negative direction. So what I'm going to do is I'm going to draw a force down here in the negative direction. And that force is going to be W. Whoa. I hate this. I've tried to get it to do something nice and neat with my drawing, but I guess it's just not interested in doing that. Maybe I'll make a thicker line and then it won't matter. Okay. So now I make what I just said was the weight is equal to, in this case, little m times g. And the fact that it's red is me trying to express the fact that it points in the negative y direction, and therefore it's a negative force. In other words, we're going to treat the component in the y direction as a negative. Now that we've gotten gravity out of the way, what's actually touching the mass m? Does anyone know?
String.
The string. And all forces in strings we call tensions. So in this case, I think you could realize that if you were, say, in an elevator car that's represented by mass little m, you would say, thank God for that cable above me or that rope above me, because otherwise me and this elevator car would fall at the rate of 9.8 meters per second, which is, problematic at best. Therefore, the tension in the rope must be pulling up on me and my little car. So that's why I'm going to draw the tension upward over here. So here is the tension. And again, because the pulley is massless and frictionless, there's no need to subscript the tension T left or T right. Okay. Now that's really all the forces acting on it. We could consider air resistance, but unless it's going super fast or it's super, super light, that they're going to be negligible. So now I'm going to say the summation of the forces in the y direction is equal to little m times a in the y direction. So that's the actual equation I'm solving. What I can see is there's a positive force, capital T, minus mg, and that's got to equal m. And I'm just going to call that A for right now, because what I want you to imagine, and this is going to be called equation 1, by the way. What I want you to imagine is that this pulley and rope situation is going to be set up in such a way that the rope doesn't stretch, nor does the rope ever become slack. Because if it became slack, then you could get a larger motion of M than the rope does. In other words, M could move by 4 inches, but the rope only moved 3 if it got slack in it. Or if the rope was stretched, the rope could move 4 inches and the mass would only move, say, 2. So we're assuming that we're not examining situations in which the rope could stretch or in which the rope could become slack. And since that's the case, if the left rope, listen to this argument very carefully. This is the physics part that sort of you need to understand. If the left side went up 1 inch, in other words, the rope and the top of the mast little m moved upward by 1 inch, then the rope on the other side, because it's not getting slack and not stretching, the rope on the other side is going to cause the top of the mast big M and the rope on the right side to go down 1 inch. If in fact that happened in 1 second, then you would say the mass little m on the left-hand side moved up at a rate of 1 inch per second on average, and the mass big M on the right moved up or down at a rate of 1 inch per second on average. Okay. Now, if in the first second it averaged 1 inch per second, but in the second it averaged 2 inches per second, then the same thing's going to happen to the mass big M. So if mass 1m in the first second averaged 1 inch per second, and then in the second it averaged 2 inches per second, well, the right mass is going to do the same thing. So there's no reason to subscript the acceleration either. That's why I just wrote m times a. I don't have to have an A left or an A right or an A sub little m or an A sub big M. Does that make sense to everyone? Okay. Now I numbered that equation, and this is important. When you get into physics, one of the things you often have to do is solve systems of equations. In other words, if you have 3 unknowns, you need to have at least 3 equations, and sometimes having more than 3 can actually ruin it and make it unsolvable. So you got to keep that in mind. If I have 3 unknowns, I have to use 3 equations exactly to get the right answer. And if I somehow get an answer with only using 2 of them, even though I had 3 unknowns, then I've clearly done something wrong. Okay, so you got to be careful with that. So that's why I number them. You can always look back and see that you used all the equations that were necessary and that sort of stuff. Now I'm going to draw a free body diagram for the mass big M, only this time, since it's the mass big M, I am going to say down is the positive direction. And this is going to be the positive y direction. This is going to be the mass big M. And I think you can see what objects are actually touching the mass big M.
string.
The string and the air. We're ignoring the air, and of course the string is relevant. And I think if you were in the box that's marked big M, you would agree that it appears you would be falling at 9.8 meters per second every second if it wasn't for that string pulling up on you. So you can probably reach the conclusion that the tension in the rope is in fact pointing upward. So I am going to, that upward, of course, is our negative Y direction. And again, like I told you before, we do not have to subscript that tension because the tension in the left and the tension in the right are the same, because the pulley's not, I mean, the rope's not going to slip, the rope's not going to stretch, and the rope's not going to get slack. Now there's a positive force. Since we've ignored air resistance, the only other force is what? Anyone? Who? Gravity. And we call that weight. And in fact, that's pointing in the positive direction on this side. So I'm going to draw a force going this way. And I really get upset at how bad these things allow me to draw straight lines. Okay, that's good. So this force right here is in fact big M G. Notice I didn't call it W because I'd already used the symbol W. All right. Now the summation of the forces in the Y direction is equal to mass times acceleration in the Y direction for big M is going to give us equation 2. And in fact, what I see for this case is big M lowercase g minus t is equal to big M times A. Again, no need to subscript A because the rope's not getting slack, the rope's not going to slip, and the rope's not going to stretch. Now, this is a system of two equations, right? How many unknowns do we have? By me listing on this problem lowercase m and uppercase m, that's me telling you, or the physics book telling you, that you can assume you know little m and big M. Not only that, when I put in G for acceleration or for weight, that's me telling you, hey, I know on the particular planet we're at, the acceleration due to gravity is G, right? So you don't have to think we don't know G. So what do we not know? How many unknowns do we have? Two, exactly. And we have two equations. So we just need to make sure we use them. Now, here's the part where we're going to do something that you did in algebra, but you probably didn't do it this way because you normally had simple algebraic expressions like 2x plus y equals 13, and then x minus 4y equals 3. And then you try to solve the system. Well, since the upper one had a 2x and the bottom one had a, let's say just a plain x, you could multiply the bottom equation by -2 and then add the 2, and the -2x and the +2x would cancel out the x's, and you just have an equation with y. So that was a little bit easier because you had numbers there. Here, I just have symbols that represent numbers, but I'm going to do the same thing. In this case, I see right off the bat, equation 1 and equation 2 have an unknown that in one case is positive and the other case is negative. So does anybody see what variable I'm talking about?
T.
Yeah, the T, the tension. So what I'm going to do is I'm going to add equation 1 to equation 2. And I recommend you write down stuff like this, because if you go back and find you made a mistake, you can go back and look and say, well, did I ever use equation 1 or did I ever use equation 2? So in this case, I just said I'm going to add 1 to 2. So T minus T is going to give me 0. And I'm going to get mg minus little m g is equal to, and I'm going to go ahead and skip a step here and say this is m plus m. Notice both of them have a coefficient a, so m plus m times a. I could have did the same thing with the other side. In fact, I'm going to do it now. I'm going to say that m minus m times g is equal to m plus m times A. Okay. And then finally, I can solve for A, and that's going to give me A is equal to M minus little m divided by M plus little m, all that times G. And I'm really bothered by that minus symbol there. So okay. And the other neat thing is when physicists do equations like this, we really like to have them solved in such a way that it's like a number with no units times a number whose units are clearly exactly the units you want. So for instance, we're solving for acceleration A, which should have units of meters per second per second. We know the variable G has to have exactly the units meters per second per second. So if I can get this equation solved in terms of G times some dimensionless quantity, I know the units work. And that's exactly what I did, is I've worked out that A is equal to M minus M over M plus M. That's unitless. All of that times G. Now, one of the key hallmarks of a good physics student and a good student in general is you want to immediately analyze any solution you get and see if it makes some physical sense. So for instance, if I hung a 20-pound turkey on the right-hand side and a 20-pound turkey on the left-hand side, what would we expect the acceleration to be, assuming the pulley is center balanced and that sort of thing?
Can you say that one more time?
Yes, if I hung on both sides of the pulley, each side had a 20 kilogram turkey, what would you expect the acceleration to be, assuming the pulley's balanced and stuff? It doesn't have a heavy side.
0.
Yeah, 0, exactly, Kevin. So if you'll notice here, if M equals M, the numerator in that dimensionless or unitless quantity is in fact 0. So that's one of those things you pat yourself on the back and say, well, that makes physical sense. That gives me a little bit more confidence that my problem solving was good, right? Now what I want to do is go ahead and solve for the tension, because that's the other unknown. And you really, once you have a system of two equations, two unknowns, once you've solved for one of them, you can plug that into any equation you want. Well, I know that I am really bad when I've got floating negatives laying around. So I'm going to choose to plug, let's call this equation 3. I'm going to choose to plug equation 3 into equation 1 because the t will be positive. Because you see in equation 1, I just got t, so I can add mg to both sides and I'd get mg plus ma. So when I do that, I now have t. I'm going to go ahead and put the mg on the other side and say is equal to mg plus m. Now I'm going to put in a, which is m minus m over m plus m, all that times g. Now immediately I can see that there's a common factor of g. So I'm going to go over here and write t is equal to g. And I sort of made that a funny g. I'm not happy with it. I've factored out the g now. And not only that, I realize that I have a potential to make some fractions. So for instance, right now, if I distribute that m, I get m times big M minus m squared over m plus m. Whereas the left-hand term is just a lowercase m, but I'd obviously like to make get a common denominator. So to get a common denominator, I have to multiply the numerator and the denominator by m plus m. So clearly the denominator is going to become m plus m, but the numerator is going to be little m times that. So I'll get little m big M plus little m squared. And now I can close off my fraction, or excuse me, my parentheses. And I think you can see some really nice cancellations. Notice I end up getting 2 times M times big M over big M plus little m, all that times G. Now, that is a true expression for the tension, but it's not expressed the way I told you, which is physicists like a dimensionless quantity times something with the known units that you have. Well, I think we generally think that of this problem as big M times G being what's rotating the pulley. So I'm going to pull out that big M and I'm going to say that T is equal to 2 little m over big M plus little m times big MG. Now you can see that clearly 2m over m plus m is a dimensionless quantity. And that mg, which is clearly a weight, is a quantity that has units of newtons, which is exactly what we expect the tension to have as units of newtons. So that's the preferred way to write it in many circumstances. Now, let's physically look at this for a second and see if that makes sense. What do you think if we actually did say little m equals big M equals 20 kilograms, okay? What would you expect the tension in the rope to be? So I've got a 20 kilogram mass hanging on the right, a 20 kilogram mass hanging on the left. What do you think the actual tension in the rope would be? And I'm actually want you to not worry about being wrong. In fact, most of the scientific discoveries come from people being wrong. So it's a super helpful thing.
Double the weight.
You say double the weight. Yeah, that's what almost everyone would say. Someone today answered the correct answer and it aggravated me a little bit. So this is why such analysis with these symbols is such a great thing, because this one actually says it's not twice that. Notice if I put in 20 kilograms, the 2 times 20 would be 40. And then the 20 plus 20 in the bottom would be 40 as well. So the 40 over 40 would disappear and I would just get 20 kilograms times G. In other words, the tension will only be one weight. And that would instinctively, like you, that would make me think this question is wrong, because clearly the tension's got to hold up 2 turkeys. So I suspect the tension should be 40 kilograms times G, but it's not. And let me show you why. Okay, so this is a new physical principle that you're learning based on the solution that we got for the Atwood machine. Now, if I actually were to, let's say, take a table, and I'm going to attach a pulley to both ends. Okay, and now I'm going to hang a rope over it. And on this rope, I'm going to put one of those little fishing string scales, which is basically just a spring that's been calibrated to move a certain amount when a certain weight's put on it. Now I'm going to put 20 kilograms on this side and 20 kilograms, not touching the table, even though it looks like it is, 20 kilograms on this side. And I might as well do it a little bit more. Oh, a little farther. Okay. Now, what I will tell you is this reading right here is in fact 20 kilograms times 9.8 meters per second every second, which is 196 newtons. Okay. Now, that's not me convincing you. That's just me telling you, yeah, you were wrong on that other answer. But now think about it this way. When I look at that fish scale and I compare it to an equivalent fish scale hanging from a ceiling, Okay. With a 20 kilogram mass on it. Would you agree that this pulley, or excuse me, this fish scale is going to read 196? Would y'all agree with that?
Yes.
Yes, and you'd be exactly right. And what do you think the force applied to the top of the pulley is? From the ceiling, in other words.
Same.
What force do you think the ceiling is applying to the fish scale?
196 Newton.
Exactly. So I think you can see from that, if you translate that ceiling to the figure on the left, you can sort of think of the 20 kilogram on the left as just doing the work of the ceiling. In which case you see that clearly 20 kilograms times 9.8 is all the tension that should be in that rope for the Atwood machine and for the two masses hanging on the side of the table. Does that make sense now? Or can you at least fathom how it is true? It might take you a little while to swallow it, but still. So that's the reality. That's a new physical principle that you probably hadn't thought of before, but it has to be that way. So we now know, in fact, that when you hang two 20 kilogram weights over pulleys like this and then put a fish scale on it, the fish scale is going to read the weight of one of them. Now, if they're not the same, it's going to sort of read the weight of the average of the two. But the main thing is, if you're assuming the weight of the scale and the weight of the ropes are insignificant, then it should be the average of the two masses, basically, because the average is what's going to pull it down, and then the other average is what's going to hold it to the ceiling. So you've got to have something holding it, and that's all the left one can be thought of as doing. So in fact, equation 3 and 4 make perfect sense with our physics. Any questions on that? All right, let's move to the next part. So I'm going to teach you a little bit about friction. So let me stop this share for a second. And you guys can try this at home. If you happen to have a heavier scientific calculator or something that's sort of sticky to your table or desktop, this has little rubber pads here. So that's pretty good. If the rubber's soft and I've got a nice sticky surface, that works pretty good. But when I actually lay it on the tabletop, say, and I try to push it, I push very lightly and nothing happens. I push a little harder and nothing happens. I push a little harder still, nothing happens. And then finally I reach a point where something moves, and then I realize it like slackens. Like I reach some force, and that was a big force and what was required to move it. But now that I got that, it's really easy to slide along. And there's a reason for that. So if I make a graph of the applied force in time of, say, any calculator or anything else sitting on a tabletop. Now I'm going to share my screen again. Almost forgot, but brain like a safe. It's okay, so I'm lying, exaggerating a little bit, but never mind. All right. So we've got a graph now of force applied. In other words, the force I'm applying over time. So if I was actually pushing that calculator, what I would see happen is the larger the force I applied, the larger the friction force would get. And then all of a sudden, the friction force would break loose and it would drop down and be this uniform force from there on out. Well, it turns out that this is mu static times the normal force, and that in fact this one is mu kinetic times the normal force. Now kinetic is just derived from a Greek word which later became a Latin word, and we picked it up It's the origin of things like if you're in physical education or in some kind of sports major, you will take some course called kinesiology. That's sort of the physics of sport. And it's just a reminder that kines means motion, kinetic energy, kinesiology. So mu kinetic means the friction between two surfaces when they're moving with respect to each other. See how my calculator and my palm of my hand have relative motion. If they're not in relative motion to each other, then that's called static friction. And from this diagram, we can see something very, very important, and that is mu static is greater than mu kinetic. Not only that, I can give us some nice equations. The equations are that the static friction, F static, is less than or equal to mu static times the normal force, and that the kinetic friction is equal to mu kinetic times the normal force. Now, there's tables, there's things on the internet that you can find that give you experimental results as to what the static coefficient of friction is and what the kinetic coefficient of friction is. The main thing is it's experimentally determined. If you looked at two surfaces at a microscopic level, say the bottom of these little rubber feet and the top of the desk, you would probably on the microscopic level see that they're really not that smooth. And in fact, they got nooks and crannies where little ridges get caught on each other. And in fact, if you looked even deeper, you'd probably find some exchange of electrons being ripped off from atoms of, say, atoms in the rubber of the calculator's feet to atoms in the tabletop. Okay, so all that stuff can be quite complicated, but it's going to ultimately give you some constant. And when you actually apply a force that's less than mu s kinetic, the kinetic friction can't, that's less than mu s times the normal force. The normal force combined with the coefficient of friction is not going to make the friction so strong that it can make the object just jump on its own. So if the maximum, for instance, for static friction is 10 newtons and I apply 3 newtons, well, the static friction is only going to apply 3 back because it's not going to just make stuff move on its own. So that's why I put less than or equal to. If I apply 1 Newton, the static friction is going to apply 1 Newton back. If I apply 2, it's going to be 2 back. If I apply 3.5, it's going to be 3.5 back. If I do 9.99, it's going to be 9.99 back. However, the instant I hit 10, which we are assuming is the maximum static friction force, which is mu static times the normal force, at that point it lets go, and then it drops down to there being relative motion between the bottom of the calculator and the desktop. And in that case, we get a constant friction that's equal to mu kinetic times the normal force. Okay. Now, we already learned about the normal force. And for instance, one of your questions in your homework, hopefully you all got this, but it was a true false concept type question. And it said, true or false, the normal force is equal to the object's weight. Now, be advised, when you get a true or false question, this should always be the case, by the way, when you get a true or false question, if you can find one instance that they didn't exclude in the actual true false question, in which it's false, then you have to answer false. You're not allowed to answer true, even though it works in every case but one. All you need is one contradiction, and that's sufficient to say it's false. So yes, that's a false answer. In other words, the normal force is not mg. It can occasionally be the weight or mg, but it's not. In fact, last time I showed you that on an inclined plane, the normal force is mg cosine theta. I also showed you that when I was pulling on a block with a box with an upward pull, that actually allowed me to decrease the normal force, so it was less than mg. If you're doing any of the problems where something's in an elevator, you know that if an object's accelerating upward, then the normal force on that object has to be bigger than mg because it's got to hold the weight of the person up, plus it's got to be big enough to accelerate the person. So that's something to keep in mind. But now that we have this big concept, one, I now know how to calculate friction. If there's no relative motion between the two surfaces, then I look up the the static coefficient of friction for the two materials, let's say rubber and asphalt. And they have that. In fact, if you work hard enough, you can find listings of different types of vulcanized rubber having different coefficients of friction with asphalt or concrete. So for instance, when you're on 64, you actually see white, sort of whitish, tannish colored road. That's actually concrete as opposed to asphalt. When you see that black stuff that they pour out that smells so horrible, that's actually asphalt. And the coefficients of friction between rubber and asphalt is very different than the coefficient of friction between concrete and asphalt, or rubber and concrete. So you can not only get that fine, but you could also differentiate if you had the resources like a national laboratory to do the experiments, or if you worked within the car industry, or if you worked for Pirelli or Goodyear or something like that, you'd probably even be able to find the coefficient of static friction between the rubber of a Pirelli tire and asphalt versus between the rubber of a Goodyear tire or a Toyo tire and asphalt and concrete. So that's something you can look up. Now, with that in mind, there's also a big learning of a physical concept here. Static friction being bigger than kinetic friction is a big deal in terms of driving. So let me ask everybody this question. When you're driving down the road, is the friction between the bottom of your tire and the road surface, is that static friction or is that kinetic friction?
Static.
Very good. That's 2 classes in a row. You guys got that right. That's actually something that a lot of people get wrong. Those that didn't answer that are still a little skeptical, I'm going to quickly show you proof that it is. So let's imagine a tire of a car. Okay. And oh, that was a beautiful tire. Okay, so there's a tire of a car. Now, if the car were riding down the road at 60 miles per hour, I think you would agree that the velocity of the axle with respect to the earth is equal to 60 mph, and I'm choosing the right hand direction to be positive. So I think that what I've written there makes sense. Would y'all agree? If the speedometer is reading 60, then clearly the center of the wheel and therefore the axle is moving 60 miles per hour to the right. Does that make sense?
Yes. Yep.
Now let's imagine we do this magic trick where we've got this forklift that can go, let's say 70, 80, 90 miles per hour. And I come up right beside your car and then pick up your car that's going 60 miles per hour with the forklift. Okay. And now I just say, okay, how fast is the bottom of the tire, which I'm going to write right here. How fast is the bottom of the tire with respect to the axle? So I'm going to say velocity of the bottom with respect to the axle. So now I'm just saying with respect to the axle, another way you can think of it is let the forklift that just picked up your car come to a complete stop. And now it's just like you're on a lift inside of a service station. The speedometer would still think you're going 60 miles per hour. So how fast do you think the treads of the tire are going with respect to the car on the bottom?
The bottom, it would be going opposite.
Exactly. But still 60, right?
Yeah.
So yeah, I would call that negative 60. And would you or would you not say the top up here would be positive 60? That's the velocity of the top with respect to the axle is equal to positive 60. Does that make sense?
Yes, sir.
Okay. Now our relative velocity equation was the velocity of A, according to C, is equal to the velocity of A according to anything, long as the middle's matched, plus that same thing again, because the middle's matched, plus that last thing. So that's the relative velocity equation. So what I'd like to know is, what is the velocity of the bottom of the tire with respect to Earth? Okay. Now that means, according to the formula above, that I can write B here, and long as I put the middle things the same, that'll be fine. So I'll just leave a blank there for right now. And then I have to say V and put that blank in there, because that whatever's in that blank's got to match the other blank. But what's on the end of the first letter has to be the end of this. So the E has to go in there. Do we have anything that has a B as the first part, or anything that has an E as the second subscript?
The bottom of the tire, BA,
Uh-huh.
and then the axle itself is AE.
Exactly. So we can put in the A here and the A here, and we're golden, right? And this is all one dimension. So the vectorness is just being met by the fact that they're positives and negatives. So I'm going to say the velocity of the bottom of the tire with respect to the axle is, of course, negative 60 mph. And the velocity of the axle with respect to Earth is positive 60 mph. So now I've proven, in fact, that the velocity of the bottom of the tire is, in fact, 0. So this is static friction. Okay. Not only that, you can also see why mud flaps and stuff like that are really good, and wheel wells are really good, because if you do the same thing for the top of the tire, you'd see that the top of the tire is moving at 120 miles per hour. So, you know, like tractors that ride around with the top of the tire exposed, or cars that have the top of the tire exposed, they can actually send rocks at great speeds. If you're going 70, you're sending rocks possibly as high as 140 miles per hour. All right, now that we have that settled, I'm going to tell you, in terms of physics, why the weatherman, when it snows, will tell you to turn into the skid. It's badly referenced in the movie Cars, where they say, if you want to turn right, you gotta, if you want to go right, you gotta turn left, or some stupid stuff like that. They did a horrible job explaining that, but the actual result they were saying was right. So I'm going to give you an idea. So let's imagine a road on a curve. So here you are going around a curve in your car. Now, what I'm going to say is your car is this, and of course, their intent is to go around this way. So you expect the tires to be slightly turned from parallel to the car, right? That's sort of normal. I actually over exaggerated by making the tires turn too far to the right, but I was doing that so you'd see that there is some turning to it to make it go in the right direction. Does everybody agree with that drawing?
Yes.
Now, if all of a sudden you hit a patch of ice, then your tire, or excuse me, your rear wheels will slide out like so, and your vehicle would be aligned like this. And in fact, it's impossible at this point for your tires to have static friction, because they're all going in the wrong direction. It's not 60 plus negative 60 anymore. It's, you know, a vector equation where you're adding one thing going north and you're adding another thing that's going north northeast, or north or excuse me, east northeast, or something like that. So as those tires are right now, you're out of control. There's nothing you can do. Now, if on the other hand, you actually catch it in time, and the car has in fact started skidding, the back end going around like this, okay? So that state that we showed in the red, if I don't wait too long, if I don't dilly-dally, if I immediately can turn my steering wheel so that the tires are parallel to the actual road, then they have a chance to reignite static friction. So if not too late, then we regain static friction. So answer this: the rear of the car slid to the driver's blank side. So I want right or left. So that you can look at either the red one or the blue one. That shows you that the vehicle was going forward and the back end slid out. Is that the driver's left-hand side that it slid towards, or its right-hand side? Anyone? I think I got somebody in the chat. Let's check. Yes. I know what you meant, Keft. So yes, you're right. It would be a skid to the left. So I'm going to write that in there and say left. Well, I'll start it like this. See, I was picking on you for writing Keft, and I ended up writing Eft with no L. All right. So now answer this question. So that was number one. Number two, in the blue car case, in which direction has the driver, well, left off a D, turned their steering wheel? So again, right or left? Actually, I'll just put a question mark here and I'll just leave it like an answer. That makes sense. Exactly. So the answer again is left. So that's what we mean by turn into the skid. So the weatherman will actually literally say, hey, turn into the skid. What he's meaning is, hey, if you're going around the right-hand curve, there's a chance, because most cars have their engine in the front, so the normal force is larger under the front wheels than it is under the rear wheels, and the rear wheels will tend to slide out to the outside of the curve. In other words, they're obeying Newton's first law of motion, which says, hey, I was going straight ahead, and then all of a sudden you asked me to take a right. I can't do that because I don't have enough friction force pushing me to the right because my rear end's so light. So the rear end of the car will slide out to the left. And as it does so, you want to turn your steering wheel to the left in hopes that you can turn your wheels far enough to maintain static friction between the bottom of the tires and the ice. If you do that, then you've got a much higher probability of not running off the road or running into an oncoming car or all sorts of bad stuff. So that's the beauty of mu static being larger than mu kinetic. Does that make sense to everyone? All right. So now that I've got that, I can actually apply this to a problem regarding friction. So here's my problem. I am going to say I have a surface right here that has mu static equal to 0.30. And that's going to be basically like a tabletop surface or something. Okay. Now, on top of that, I have, let's say, a blue box whose mass is big M equals 100.0 kilograms. And then on top of that, I have a small mass whose mass is 50.0 kilograms equals lowercase m. Now, in addition to that, I've got a rope running over here, and I've got another rope running over here. And in fact, they are going around a pulley that is attached to, let's say, this wall right here. Okay. What I would like to know is what is the minimum force I can apply to that? And what I need to include here is this. So the static coefficient of friction between the red box and the blue box is only 0.2, but the one between the blue box and the ground is 0.3. But I want to know what minimum force can I apply to make this be able to accelerate at all. In other words, just have the acceleration be willing to change from 0 to something other than 0. Okay. So that's not a trivial problem. I am going to start off by drawing a free body diagram, as I often do. And I'm going to try to make the free body diagram be consistent from one diagram to the next. So I'm going to say this is the positive x-axis, this is the positive y-axis. And in fact, I'm going to say that this mass right here is mass little m equals 50.0 kilograms. Now, at this point, you can completely work it in terms of 50 and 0.2 and 0.3 and 100. I'm going to work it in symbols so we can see some results. So instead of asking you, I'm going to have to just put a little put a little speed in here and say the forces myself. So in this diagram, I can see that the tension is causing a force in the positive x direction. That's the tension. And for the same reasons as last time, the tension is not going to be any different on the red box than it is on the blue box, other than, like we said before, the difference in directions. I'm also going to have a normal force acting in the positive y direction. That's going to be F normal sub little m. Okay. I'm also going to have a weight in the negative y direction. That's going to be W is equal to little m g. And as I am pulling to the left with a FM in, that's going to tend to make the 50 kilogram mass try to move to the right on the 100 kilogram mass, which means friction is actually going to act in the negative x direction. And this would be F static sub m. Okay. So I can say the summation forces in the y direction equals mass times acceleration in the y direction. And what I'm really going to do, well, actually, in this case, the acceleration is just 0. We're assuming the block's not going to be bouncing up and down. In fact, the box is not going to, neither box is going to move at all in the vertical direction. Not now, not later, not later. So the acceleration is 0. For this case, what I'm going to get is Fn sub m minus mg has got to be equal to 0, which gives me equation 1 that says that Fn sub m is just lowercase m, lowercase g. Okay, so that's not one of the things we were asked for, but that's something we're going to need to be able to do. Also, I have the summation of the forces in the x direction equals mass times acceleration in the x direction. And that's the one we're eventually going to take the acceleration equals 0, but I'll just leave it there for right now. What I have is that the tension acts in the positive direction, but the friction static sub m is going to be in the negative direction. And I'm going to say that's equal to m times a. But remember, I'm going to eventually allow a to be 0 because that implies F min. So this will be equation 2. Now I'm going to draw another free body diagram for the big mass. And that's going to be X is pointing to the left now, because the little red mass moving to the right is equivalent to the blue mass moving to the left. So what I see is I'm going to have a force F min acting this way. I am going to have a normal force, just plain Fn. Notice I had subscripted the other one with a lowercase m, so I don't have to subscript this one. I'm still going to have the mass there being big M. I also have, in this case, I'm pulling it to the left. That's going to tend to make the tension pull to the right. So I'm going to have a tension this way that should be exactly equal to the other tension. Now I also have, acting in the negative direction, I have the weight, which is big mg. Notice I didn't put W there because I'd have to subscript it. But not only that, Newton's third law applies. So if the 50 kilogram box has a normal force of Fn sub m, then the 100 kilogram box is supplying that and therefore feels a downward force of Fn sub lowercase m. Ooh. So that's Fn sub m. Not only that, there's a friction force acting on the 50 kilogram block. Since the block below it's being pulled to the left, the friction force on the 50 kilogram block, which was pulling to the left, is actually pulling to the right on the bottom box. So I'm going to say there's another red force this way. And that's the friction force static with a lowercase m there. Okay. And not only that, since I'm trying to get the thing to move, there's also going to be a F static that I'll just call F static without the big N or without the big M, because I did subscript the other one, so I don't need it for this. Okay. So now I've got all these forces and I can write Newton's second law. The summation forces in the y direction equals mass times acceleration in y direction. In this case, I'm going to get F normal minus big M G minus F in little m, which we already discovered was lowercase mg, so that'd be minus mg. So from equation 1, so we've already used equation 1. This is going to be equation 2, by the way. I've got big mg downward, I got normal downward. So in fact, that should be it. I don't see any other vertical forces. So we're going to set that equal to 0. And that's going to give us that the normal force is actually equal to m plus m times g. which of course you can actually work out to 150 times 9.8. Okay, so that's going to be called equation 2 prime, which is just, just the same thing as 2 basically. All right, now we have the summation of the forces in the y direction, or excuse me, in the x direction, equals mass times acceleration in the x direction. So in this case, I've got the minimum force, F min, minus the friction static, lowercase m, minus the friction static period, and then minus the tension. And okay, I have not yet solved equation 2 for the tension. In fact, dang it, stop this. In fact, this equation should be called equation 3. I forgot I'd already used equation 2. So let me do this. So that's equation 3 prime. Now we're back where we started from. Okay, so that's all that. And in fact, for it to be minimum, I have to set that equal to 0. So I can now say that Fm or F min is equal to the tension force, which we already decided with A equals 0 is just going to be the static friction of the mg of the lowercase m. So that's going to be mu sub s sub m times the normal force for the other one, which is lowercase m times g. So that takes care of this term. And now I've got to do the static force due to the big mass. Now, in that case, it's going to be plus mu static, plus mu static. In this case, it's not subscripted, it's the 0.3. And then it's times the big M plus little m times g, because that is from equation 3 prime. And this was from equation 2. Okay. And then I've got plus the tension, and the tension turned out to be yet another mu s times m times g. So in fact, the minimum force that you have to apply is 2 mu static m g, and that's mu static sub lowercase m, times mu static m plus m times g. I think we can see that you end up getting, I think it's 196 plus 249 newtons. I'm going to put a question mark by that because I'm just remembering doing those calculations earlier, but I do know this is the equation that I got. Okay. Now, time's actually up. There is a problem in my YouTube channel that actually does the one that I was planning on doing. So let me pull that up real quick. I think it's literally called Fuzzy Dice or something like that. So let me do a search for that. You guys are welcome to leave. I'm going to wait here for the last person to leave in case anybody has any question. Yes, the video is called Applying Newton's Laws, Normal Force, Elevators, Fuzzy Dice, Atwood, and the Clothesline. And that was from 1 year ago. So, in fact, let me do this. So this is the video where I do the Fuzzy Dice one. That's really all I wanted to show you in addition to what I've done. I might still do it next time, but at least now you can look at this particular example, which I'll put in our actual Canvas module for this week, and you should be good to go. So that's it. Anybody have any questions?
Where did you get the?
Where did I get this video, or where did I get something that I did on that problem?
on the problem.
Okay, all I did here was I did a search for dice, and you're breaking up in the middle, but I did a search for dice on here, and that's what came up. In case you were asking about the other problem, I will share screen with my iPad again. So there you go. Is there some part of that you didn't get? Is that what you're asking about? Whoever
Yeah,
asked
for the F-man equation, where did you get the 2?
Okay, so this one right here, and then this one right here added together to give me mu s, because what we found out from this equation, equation 2, is that the tension is equal to the static friction of the small one. So I got mu s mg already from this one. I got fs is this guy, the m plus m, and then t was this mu s mg.
I got it. I just didn't see the subscript.
Yeah, gotcha. Oh, and actually, yeah, that subscript should be there. Nice catch. You didn't see the subscript because I didn't write it, because I'm a crackhead. Anyways, yeah, I think that's what I got. Y'all might want to check your math as well, but basically it should be something like 2 times 0.20 times 50.0 times 9.80, and all that should come out in newtons, plus 0.30 times 150.0 times 9.80, and all that should come out in newtons. So that may or may not be equal to the 196, because I just noticed some things I think I might have did wrong. Anybody else have any questions? I got Kamna and Greg. Do y'all have any questions for me?
Just want to make sure about the test.
Uh-huh.
So we only done so far test number 1, right?
Yeah, test number 1 was due last night.
Okay.
And test number
I
2
think-
is due a week from last night.
Okay, thank you.
No problem.
Because I believe I did the test number 1 long before last night.
Yeah, I think most people did. I think I just kept giving extensions and that sort of thing. So
Okay.
it looks like I did get 196 for the first one. I'm doing the other one too, by the way. 0.3 times 150 times 9.8. This one's 441. That's what I didn't do.
Okay.
This one's also 2 sig figs. So I'm going to say plus 196. That gives me 637 newtons. So that should be the final answer if I didn't make any careless arithmetic or algebraic errors.
I'll double
Kamna,
check
do you have any questions, sir?
that. No. Have a good one.
You too. Thank you, sir.
Mhm.
Bye-bye.